Hello, everybody. Hi, thank you so much for being here today. Depending on where you are, it's a good morning or a good afternoon or good evening. This is our seventh installment in our webinar series, Electrochemistry in the TEM. My name is Jen McConnell. I'm the product manager here at Protochips, where we create solutions for in situ TEM powered by machine vision software. For those that are joining us for the first time, this series is focused on using our Poseidon liquid cell system with electrochemistry for performing nanoscale electrochemical experiments in the areas of batteries, corrosion, and catalysis. And the results are then used to complement bulk scale analysis to tell a complete scientific story. Our Poseidon product line has been in the market now for over 10 years, where it's matured and it's evolved with the feedback from the field. And now our users are publishing relevant and impactful nanoscale electrochemical studies at rates faster than anyone else. And many of them are experts in nanoscale electrochemistry in the TEM. And today's speaker is no exception to that. We have a couple more webinars left in this series, so please feel free to sign up so you don't miss the chance to ask questions live to our expert users. I put the website in the chat for you so that you can go ahead and register for the last two after this one. A couple housekeeping items before I introduce the star of the show today. First of all, everyone is muted. We've got quite a large attendance for these webinars, and so we've got everybody muted. But please, if you have questions, and we encourage questions, enter them in the questions box in the GoToWebinar interface. And at the end of the talk, I will read those questions out to our speaker so that he can answer. And then there'll be a very short survey that pops up at the end of the webinar. If you don't mind filling that out for us, we would be very grateful for that. But okay, I'm not the star here today. Let me introduce Professor Yifei Yuan, who's our star today. Professor Yuan is currently a professor at Wenzhou University in China. He obtained his PhD from Michigan Technological University under advisory of Professor Reza Shabasian Yassar, and used to hold a research professor position at the University of Illinois, jointly at Dr. Khalil Amin's group at Argonne National Laboratory. His research focuses on fundamental studies of electrochemical energy storage materials using electron microscopy. He investigates local atomic and nanometric structure property correlations to elucidate design principles for advanced energy materials by rational syntheses, advanced characterization, and integration of material engineering strategies. He's published approximately 150 papers with an H-index of 55. So we've got Professor Yifei Yuan. Yifei, thank you so much for joining us today. I'm going to go ahead and hand the controls to you, and I will be here for the question and answer session at the end. Thank you.
Okay. Thank you, Jennifer, for the introduction, and thanks for the Protochips organizing this webinar, so that I have the chance to introduce to everybody the work that me and the Professor Reza Yassar back in University of Illinois Chicago. We did a lot of in situ TEM microscopy on the battery materials, and specifically this one using in situ liquid electrochemical TEM to observe the lithium-oxygen battery reaction kinetics. And let's move to the next page. So the reason that we study lithium-oxygen battery, first of all, it has the highest energy density among all these secondary rechargeable batteries in the world so far. And as you can see in the table, it shows far more, much higher capacity and energy density compared to the current lithium-ion batteries, and also the emerging sodium-ion batteries and the lithium-sulfur batteries, and even sodium-oxygen batteries. And the working principles of this battery is quite similar to the lithium-ion batteries, except for the cathode side. It requires the presence of a porous cathode material, which can allow the electrolyte to penetrate through the pores, and also allow the oxygen molecules to dissolve and diffuse through the pore structures to react with the lithium ions and get reduced on the surface of the cathode particles, which is typically carbon materials loaded with different catalysts, such as noble metals, the non-noble metals, and also transitional metal oxide. They are used as the cathode catalyst to boost the reaction kinetics. But practically, this battery has a large drawback, which is the very sluggish reaction kinetics. As you can see from the battery curve, the voltage profile during the discharge, this battery shows about over 0.5 volt compared to the theory voltage at about 3 volt. And this kinetics is even worse when during the charge process, when the discharge product lithium, which is well known as lithium peroxide, is going to be decomposed. This reaction is even more sluggish, and it gives a large over potential over 1 volt. So that means the round trip, the energy efficiency during the round trip is pretty low, which hardly hinders the application of this battery for commercial use. So in our work, we try to understand the reaction step, like what is the underlying reasons to cause this large overpotential by using in situ liquid electrochemistry, transmission electron microscopy. And we further, so because this poor reaction kinetics usually requires the use of catalyst, we further explore, so based on the fundamental understanding revealed by in situ liquid TEM, we further understand how the loading of a manganese dioxide catalyst by utilizing a surface effect can help us to efficiently tune the ORR kinetics of the battery. So this is basically what I'm going to talk today. So this is the work we published with Argonne, with Dr. Kali Amin, Jun Lu at Argonne, and also with Professor Yasser at UIC. So it briefly summarized the use of different setup of in situ TEM techniques, different setups, how they can be utilized to study the battery reaction mechanisms for in terms of the battery component, such as on the anode and the cathode side, we have this open cell, solid state open cell design, which help us to understand the reaction at a very high spatial resolution, because it doesn't require the presence of any liquid electrolyte. We basically use a solid electrolyte or an ionic liquid. So the resolution, spatial resolution, can be guaranteed. And with the development of solid state batteries, so we also designed the people also designed the thin film battery to study how the interfacial resistance cause the large problems in solid state batteries. And also in our group at the UIC, we also have the heating capabilities to study specifically the cathode materials, because when it was overcharged, it tends to release oxygen, and also cause, by thermal runaway, causing a lot of problems. And so we try to understand how the battery feels at high temperatures to understand their failure mechanisms. And lastly, but not, this is also very important, the liquid one, the liquid cell, which is I will introduce today. So this one is also very powerful to study the battery reactions in liquid electrolyte, which is widely or mostly used in most of the battery configurations nowadays. So it basically has the 2 silicon chips with they construct micron-sized cell inside, allow liquid flow in and out, and it also has the built-in electrode, typically 3 electrode systems: the counter electrode, working electrode, and the reference electrode. It allows us to make a lot of designs by the customers to satisfy their specific requirement, like the lithium-ion batteries to study the lithium deposition on the anode, or to study the cathode reactions, as I'm going to talk today. So in our work, we use the prototypes Poseidon 500, and this is a video I direct copied from the company. So it takes about maybe 1 minute, and while it is played, I think it tells everything very clearly how it works. And meanwhile, on the right side, the figures A, B, C, D shows how we customized, how we designed the cells to satisfy our research need on lithium-oxygen batteries. So we use the photolithography and the lift-off techniques we coat a lithium cobalt oxide particles on the counter electrode, which we basically use that as lithium reservoir, as a lithium source to supply lithium to the working electrode. And on the working electrode, we have the carbon electrode. Glassy carbon can be directly used as as I talked previously, it can be used as a cathode catalyst. It's porous and allows oxygen and the electrolyte to diffuse, to penetrate. So it can be regarded as a typical cathode material for the lithium-oxygen battery. And also we have the typical salt dissolved in the TEGDME electrolyte. This electrolyte is quite common in the real lithium-oxygen battery setup in many studies. So we directly use this one. And more importantly, the TEGDME has a high oxygen saturation degree, so it can allow a lot of oxygen molecules to be dissolved in the electrolyte. So this can actually allows the supply of oxygen to the liquid cell. So we also load our particles. So that's the lithium cobalt oxide for the cathode, and also we have the carbon electrode on the as the working electrode. So we can control the voltage to do the charge and discharge process. The spacer is about 500 nanometers as we used, which is a pretty large one. So this is the discharge process. It is pretty quick. This is the bright field stem imaging. It shows the particle. I think this video is speed up like by 32 times or 16 times, but it basically shows how the growth of lithium peroxide is quite straightforward on the current collector. So we basically focus on two locations. It is a common sense that the growth of lithium peroxide will happen on the interface between the electrode and the electrolyte. So that we call it the growth of attached lithium peroxide on the substrate, and that follows a conventional concept which we have widely accepted in the field. But we also noticed that in the electrolyte, which is isolated from the current collector, the growth of this particle is also active during the discharge process. So because this particle, I mean, not only this one, but a lot of similar particles, they are isolated within the electrolyte. They don't have an electron path connected to the current collector. So that means they don't contribute for the capacity. They are not the electrochemical reaction. It's more like a non-Faradic reaction. So we try to understand how this particle can grow in the electrolyte. So because prior to this work, I think as early as 2016, the same group, Junlu, Khalil Amin's group at Argonne National Lab, they proposed the presence of lithium peroxide as the lithium superoxide existing in the electrolyte as the reaction intermediate to tune the reaction kinetics of this material. But at that time, there are not very much solid proof to confirm that. But in our work, we believe this can well explain this observation. So how it is happen is for the first reaction, because we have a lot of oxygen molecules in the electrolyte, and when the oxygen molecule diffuse to the current collectors, it will directly get one electron and become the superoxygen ions. And these superoxygen ions can then diffuse to the electrolyte, and when it diffuses to electrolyte and reach a critical concentration, it will trigger a disproportionation reaction. It is a chemical reaction. It doesn't contribute for any electrons to the outside circuit, so it is a non-Faradic reaction. But this is very important because this is how we believe can well explain the generation of the lithium peroxide within the electrolyte, which is far from the current collectors. And then we analyze the growth of these two particles either on the attached surface or on the area within the electrolyte. And we found that the radius of the particles during growth, it has a very similar relationship to the, it has a, so the R is linear to the cubic square root of time. So that means the reaction, during the discharge process, the reaction kinetics or the formation of lithium peroxide, the discharge product, is highly controlled by the ionic diffusion process. And so as the one attached to the surface of the current collector, we believe that should be a lithium diffusion control process, which it requires the lithium ions to diffuse from within the electrolyte to the surface of the current collector. It has long distance, so this is the control step. But for the one within the electrolyte, it requires a higher concentration of the superoxygen ions to trigger the disproportionation reaction. So the accumulation of the superoxygen ions requires the constant diffusion of the superoxygen ions from the surface to the electrolyte. So that is the diffusion, the controlled step for this growth mode. During the charge process, which we flip the voltage to trigger the decomposition of the lithium peroxide, and so in this video, so all these particles attached to the surface are lithium peroxide, and we focus on several regions. The first one is also the ones that, as shown by the orange arrows, that's the particles attached to the carbon collector surface. Their decomposition, as we can tell from the image, start from the interface between the current collector and the electrolyte, not from the regions just contacting the electrolyte. So that means the area that is first decomposing is at the current collector interface. So that means the limiting factor might be related to the sluggish electron conduction from the lithium peroxide bulk to the current collector. We also notice the decomposition of the particles isolated in the electrolyte, as indicated by the black arrows. So this is one example. We actually have multiple examples, but for the one specific one, the black arrow indicated one, we found a very common phenomenon that the decomposition of the particle always starts from the region that is directly facing toward the current collector, while the other side that is far from the current collector, it will not decompose first. So that actually is very repetitive, and we try to understand why this particle start decompose from the region that is closer to the current collector. So that also means, it must be related to the diffusion distance of the ionic species. So if we record the presence of the superoxygen ions, we propose these reaction steps. So the first one is the compropionation reaction, where the lithium peroxide plus 1 oxygen molecules is going to become a 2 lithium ions and 2 superoxygen anions. This is non-ferritic reactions, so this allows this reaction to happen within the electrolyte. They don't need to be connected to the current collector. And these superoxygen ions then diffuse to the current collector, which we will not be able to see that because it's dissolved in the electrolyte. But when we contact the electrode, it will get an electron and get reduced to the oxygen molecules. So in this process, the diffusion of these superoxygen anions is the limiting factor. So this also causes the initial decomposition area is always on the in the region where it is closer to the current collector, because the superoxygen anions has a shorter diffusion distance, so it can be decomposed faster. And based on these observations and our previous theory work, to proposing the existence of the superoxygen anions, we further came to these reaction mechanisms. During the discharge process, there are 2 reaction modes. First, on the surface of the current collector, which is a lithium diffusion controlled process, while within the electrolyte, the growth of lithium peroxide can also happen, and it is controlled by the diffusion of the superoxygen anions. And this process is quite reversible. I mean, the reaction kinetics is reversible on the charge process, where the specific limiting factors continue to play their role. So as a conclusion in this work, we use an experimental method to support our theory that the lithium superoxide or the superoxygen ions, it functions as the critical intermediate product during the oxygen reduction reaction and also the oxygen evolution reaction. And we further revealed that the reason for the sluggish reaction kinetics, particularly on the OER process, which, as I previously showed, it shows a large error potential over 1 volt. So we believe that sluggish reaction should be originated from the diffusion of the superoxygen anions, which controls the overall step. And this actually provides some guidance to the electrolyte design. So if we can design some electrolyte that is more favorable for the diffusion of superoxygen anions, that would greatly boost the reaction kinetics of the overall battery system. And also guided by this concept, this design, we try to further consider if for the superoxygen ions, because it can be easily absorbed onto a lot of catalyzed surface. So if we can design or modify using the surface engineering strategy to modify the catalyzed surface, maybe we can control the absorption of the superoxygen species. Maybe that can help us to control the overall reaction process. And then we came up with this idea. So manganese oxide is a quite common catalyst in both the high temperature catalysis or electrochemical catalysis. And because it has a lot of the oxygen dendroning bonds on the surface, and so its catalytic reactivity is quite high. So in our work, we try to first using the surface engineering strategy to synthesize two manganese dioxide particles. They are the same phase, but they have two different morphologies, so as to have two different dominated surface exposed, as the the different exposed crystallines as the surface, crystal plans at the surface. And we use a simply potassium chloride solution to control this process. And we further try to understand what are the exposed facets, their crystalline index. Then we combining scanning electron microscopy, which help us to get a 3D sense of the morphology of the particles, and also help us to measure the angles between each surface, like this like rod-like, and also this plate-like. And we also combining ultramicrotome to cut the rod along their growth direction, so we can directly identify their lateral surface as shown in D and E. So this actually helps us to identify the exposed facet of these two materials, of these two samples. So we finally realized that the rod-like particle, it is dominated by the 100 surface, while this plate-like surface particle, its surface is dominated by 111 surface. Then we use these two particles as the cathode catalyst to see how we can, if we can, tune the reaction kinetics. And on the discharge process, they show similar effect, but on the charge process, the one that is reached on the reaching the 100 exposed surface, it shows a better OER catalytic properties compared to the black one, the 111 dominated MO2 catalyst. So we further analyze the discharge product, the morphology of the lithium peroxide on the surface of the two particles. So for the rod-like particles, as formed lithium peroxide particles, they more like a film-like. You can see it's like it's uniformly coated on the surface of the particles. But on the for the 111 surface dominated particles, we see a lot of these donut-like particles, lithium peroxide, and it's a toroid-like, either one. So usually, for the thin film morphology ones, it shows a better OER kinetics, because for the thin film ones, it is closely connected to the surface of the catalyst, so it will be exposed to more active sites to be get easily decomposed during the charge process. This is why the 100 surface, it has a much better OER kinetics. But then we try to understand why why the morphology of the lithium peroxide is different on 100 and the 111 surface during the discharge process, and what is the determining factors. We realize this might be tuned by the intermediate lithium superoxide in terms of how it reacts with two different surfaces. So we have our collaborators from also from Argonne Group and also at UIC. They carried out a very simple calculations. So these two images shows the most stable configurations of lithium superoxide molecular when we come in contact with the either 100 or 111 surface of MO2. And the calculation shows that on the 100 surface, it has a much lower absorption energy compared to the 111 surface. So that means when we have the lithium superoxide superoxide anions, the molecule, the species, the intermediate species can be more easily attached to the surface of 100, or is more tightly attached to the 100 surface. And actually, so the lower part, this simulation work is also from a collaborator, Professor Saiful Islam from University of Bath, which is now professor in University of Oxford. We have collaborated a lot of battery works, but this is the earlier work of his group. It shows that the 100 surface is more easily to generate oxygen, the oxygen vacancies. And if we have oxygen vacancies, that means the it enrich the surface physical chemical properties. That can also lead to a higher catalytic activity of this material. So based on that, we came to this conclusion that when we have the 100 surface and compared to the 111 surface exposing as the catalytic site, it actually results in two different reaction mechanisms, which are well known in the field. One is the surface mechanism, where we have the oxygen molecules came in, get one electron reduced to superoxygen ions. And these superoxygen ions, because on the 100 surface, it can be tightly absorbed on the surface. It cannot go to the electrolyte, so its coverage on the surface is quite uniform, and gradually the lithium superoxygen oxide can go through this propionation reaction and become the lithium peroxide. This is how the thin film like product form. But for the 111 surface, when the oxygen molecules get reduced to lithium superoxide materials, its absorption on the surface is not strong enough to bond the molecule. So the superoxygen ion is more likely diffusing to the electrolyte, and in the nearby region, when its concentration is reaching a critical limit, it will go through this disproportionate reaction to become the lithium peroxide. And this is also how we observe the formation of the lithium peroxide particles within the electrolyte. So in this work, we show that how we can actually to tune the reaction kinetics using the fast engineering strategies on this very low-cost manganese oxide catalyst. So to summarize, in this work, we based on the in situ transmission electron microscopy, a fundamental understanding to efficiently tune the surface reaction mechanisms versus the solution mechanisms using two exposed surface of manganese oxide to demonstrate this concept. I think I still have like 10 minutes. I can talk a little bit more about some other works that we use to study, using the liquid TEM to study material science. So the first one is the lithium-oxygen battery. I just talked about this one. The second one on the top right corner, this is the one we study how the gold nanoparticles grow on the two-dimensional substrate in its aqueous salt environment. And also we studied some work on the calcium phosphate mineralization process. So this process is related to how a tooth cavity is formed, in our tooth enamel, and we also studied some material behaviors in aqueous electrolyte to see how it is decomposed. So this one is also a manganese oxide. So during the in the electrolyte environment, we observe how it goes through a misorientation and also a detachment mechanism to be decomposed. So here's the growth of the gold nanoparticles on 2D substrate. So the application of this, the background of this research is, in the field there are a lot of study focusing on growing the noble metal catalyzed nanoparticles on the surface of two-dimensional substrate like graphene, molybdenum sulfide, like the one we used here. So the key question is how we can understand how gold nanoparticles are developed, are formed, nucleate, and grow on the surface on the substrate. So here we use the liquid TEM. So this is not an electrochemical one, just liquid TEM, a very simple setup. And we flow in the gold chloride aqueous solutions and use electron beam to reduce the gold and to trigger the nucleation and the growth of gold nanoparticles on the surface of substrate of MOS2. And so this is the video, I think, can be played. Okay. So we initially see a lot of tiny nanoparticles formed on the surface of MOS2, and then these tiny, and some particles are large, some particles are small, and then we see the small particles somehow tend to disappear, but the large particles will tend to grow bigger and bigger. And then we use the snapshot TM images on the right side to highlight this trend, and we aim at different locations to highlight how an Osterroth ripening mechanism actually dominates the growth of gold particles in this situation. You see the smaller particles get disappeared, while these big ones, these big particles grow bigger and bigger at the expense of the smaller ones. And we have multiple regions to confirm this, and so now we can came to this schematic to summarize this mechanism. And also, this is more recent work. We studied the mineralization process of hydroxyapatite, or HA in short. So this is a minerals that exist in our tooth enamel, and its reaction equilibrium is very important to maintain the health of our tooth. If something goes wrong, like the nucleation growth process, is not in equilibrium, or is disturbed by some incoming species, then we can develop a tooth cavity and cause a tooth disease. So in this work, we try to understand how what is the mineralization process of this HA. So we use artificial saliva. We make this solution by referring to the typical recipe of the saliva in our human body, and the setup is quite similar. This is the simple liquid TM without electrochemical capabilities, and the interesting thing is that we, in addition to the classical nucleation pathway, which is the direct HA nucleation from the solution, you can see how the particles get reduced, get nucleate and growth by attaching each other and grow bigger and bigger. This is what people have largely known in the field. But more importantly, we show that we observe another phenomenon, a non-classical pathway, where the HA can nucleate at the surface of the amorphous calcium phosphate, which we call it ACP. So the bright ones are the HA crystalline material, while the larger sphere with a faint brightness is the amorphous calcium phosphate. So from the video, you can see how the particles nucleate and grow on the surface at the expense of the ACP. And from the snapshot TEM images, for example, in figure C, we showed how the particles can actually coalesce together to contribute for the growth of the particles. And then we also see the detachment of the H nanoparticles from the ACB substrate. When they grow sufficiently bigger, they will be detached from the surface to the electrolyte, to the solution. Okay, I think that's all the research work I want to show to the audience today. And finally, I want to thank Professor Reza Yasser, who is also my PhD advisor at UIC or at Michigan Tech. And we have a lot of capabilities doing in-situ TM at UIC group. And also thank our collaborators from Argonne National Lab, also my second group. They helped to design a lot of battery reactions. And also these three excellent students, the back then students, Kunhei, Wenzhou, Yuan, and Bao Song. So Kunhei did the liquid TM for the lithium-oxygen battery work, and also the HE minorization work, and Wenzhou did the surface engineering work, and also Bob he did the work of the gold growth molybdenum disulfide. And finally, I want to introduce our university by taking a few extra more minutes. So now I working at Wenzhou University in the city of Wenzhou in China. It's a southeast city close to the northeast to the Southeast Sea, China. And I have established our group at Wenzhou University. We focus on the microscopic study of battery materials. And in addition, I also want to introduce a international journal, Carbon Energy. It's a widely journal, and it focuses on the advancement of advanced materials and technology for clean energy and CO2 emission reduction. And now it has an impact of over 20, and I'm honored to be an associate editor of this journal. And if you have very good work, and you can submit to our journal to help the to advertise the science in a more broader readership. And with that, I want to conclude my talk. Thank you very much.
Professor, thank you so much for that great talk and introducing some of your more recent liquid cell work. That's really interesting. If there are any questions, please go ahead. Now's a great time if you have not had a chance to enter them in yet to the questions box. Go right ahead, and I'll start asking you the first ones that we've got here. We actually have several questions surrounding the chip preparation for the batteries. So a lot of people are curious if you can explain in more detail the deposition method for the lithium cobalt oxide onto the counter electrode. They want to hear a little bit more about how you deposited it, how you knew how much to deposit. I think there's a lot of people interested in customizing the counter electrode material. So if you could talk more about that process.
Yeah, okay. Well, that's a very good question. And actually in our work, that is the most challenging part. I mean, we deposit a lot of, we tried a lot of times, but the deposition is not that successful at the very beginning. And this work, because for the deposition part, we have a very specific person, an author from UIC who did this work. And I believe we talked a lot of details in the paper, in the details. Yep. So we use the we use the photolithography and also the lift-off techniques to prepare this material. But for this technique, I'm not quite familiar, to introduce this technique. And maybe we can refer to the paper for more details.
Is there a particular author from the paper that we can?
That is Tara. I'm not sure if you can see the
Yep.
The paper. Okay, it's Tara Corrosion. Yeah, it's also a group member from our UIC group who is an expert in the clean room capabilities.
Perfect. Yeah, we've had.
Yeah, I'm sorry for that.
No, that's okay. That's great. We've had a lot of questions come to us about that same, how can we change the counter electrode materials and customize it and such. And so that was a very interesting part of the paper. Thank you for sharing.
Yeah, I want to add maybe a few more explanations. So initially we tried to build a very authentic battery using lithium metal anode, but the lithium metal deposition is more challenging. And then we realized, for the in-situ TEM setup, we have to sacrifice a lot of real battery situ conditions requirement. So as long as the the lithium source, the lithium cobalt oxide is just used to supply lithium, is not like to do other things. It's just to supply lithium ions to the counter electrode. We believe this can largely reflect the situation. We initially tried to use the lithium metal, but that is more challenging, something very hard to achieve.
Do you feel like there were significant sacrifices made by using lithium cobalt oxide instead of lithium metal?
I'm sorry, satisfy? What do you mean?
Do you feel like you had to make sacrifices? Were there by using lithium cobalt oxide instead of lithium metal, or do you feel like the results in the end were probably comparable?
I think the result because we do the charge and discharge, we see that battery can actually work, and we can see the reversible formation and decomposition of the material, and also we also make some other compromise, like we use galvanous with a potential stat discharge-charge process instead of a galvanostatic, so we just try to make sure the lithium ions can be supplied to the reaction to the cathode region of interest from the counter electrode, and so yeah, there's a lot of sacrifice we have to make, and to make this battery work actually.
Yeah, I understand. You're miniaturizing it so small. Next question, there's a question about what carbon did you use as the working electrode and how did you put it there? So do you want to explain a little bit more about the chip itself?
That is the glassy carbon electrode.
Mm-hmm.
Yeah, I think that one is when we purchase it, it has the glassy carbon already.
That's right.
We directly use it, right? Yeah. I mean, maybe you are more familiar. I mean, you should have, like, the company should have this kind of electrode, right? We purchase it and we don't do anything on the anode side, if I remember correctly, on the working electrode, I mean.
Yep, that's correct. I wanted to let you answer the question instead of me, but yes, the chip comes with the glassy carbon working electrode, so you don't have to put it there. We sell that as a product.
Yeah, that's a good thing. That's actually a good thing. Yeah, we can directly use it.
Thank you.
Maybe that is not a. I mean, maybe that is not a very typical cathode material, but I see a lot of people use graphene or some other kind of carbon materials, but I mean, since back then we have this carbon electrode, so we directly use it and it works.
Yeah, it's definitely our most popular selling chip for electrochemistry is with the glassy carbon instead of platinum for working electrode. The next question asks, so for the lithium-oxygen experiments, did you saturate the electrolyte with oxygen?
Yes. We bubble in oxygen molecules into the TEM electrolyte overnight, I believe. So that takes a longer time, but that can guarantee the oxygen. There's a lot of oxygen dissolved in the electrolyte, so the reaction will not be limited by the shortage of oxygen within the miniature cell.
Okay, great. And then there's a question asking about what kinds of tests did you perform to understand the influence of the electron beam? And did you look at the influence of the electron beam?
Yep, I think we control the beam to use the turn on off experimental method to observe the decomposition in the experiment and the decomposition and the formation of the lithium peroxide. And that beam effect can be excluded largely. And more importantly, we see that because when we do this work, a lot of the comments from the reviewers, they ask whether this formation of this thing is caused by electron beam reduction. And because when we flip the voltage, we see the particles, it can be decomposed, it can form during the discharge, and when we flip the voltage, it can be decomposed. So comparing the beam on and off experiment, that makes us to believe the electron beam effect is not that significantly affecting the reaction.
Okay, great.
Mm-hmm.
Let's see. Okay, we've made it through the questions that were submitted. We do have one audience member that wants to have a more fluid discussion with you. So I'm going to connect you with him afterwards. And so that way, if you have time to have a discussion, he's got a few questions for you. He wants to talk to you live. But thank you so much, Professor Yuan, for joining us today and for preparing this talk and teaching the community more about battery research in the TEM. We really appreciate it and enjoyed it very much.
Okay, thank you, Jennifer, and thank you, everybody.
Yes, thank you, everybody, for joining. Have a great rest of your evening or your day, and we will see you for the next one. Thank you.
Okay, thank you.